Hello everyone, welcome to the third lecture in this course. So in the previous lecture, we looked at the very fundamentals of solar radiation in terms of how we characterize the sun as a black body radiation source, what is the temperature of the photosphere for this consideration. Accordingly, how does the solar spectrum look like, where does it peak, and what is the surface luminosity of the sun, what is the total power emitted by the sun. And then further, we looked at the different planets in the solar system. So, if you are at a distance d apart from the sun, then what would be the surface luminosity or the solar radiation intensity at that particular point. So, today we will delve further into the fundamentals of solar radiation, and we will look at the atmospheric effects which come into play and which change the nature and quantum of solar radiation which we receive on the surface of planet Earth. So, as we calculated in the last lecture, the mean radiation at the Earth sun distance that comes somewhere around 1370 watt per meter square. So, that has been defined with more precise estimations and calculations, that has been defined as the solar constant. And though there is a little bit of variation in the different literature sources, if you look at different books or research papers, there might be very small variation in the value of solar constant here and there, but one globally accepted value is around 1366 watt per meter square. So, that is the solar constant, which is basically the solar radiation intensity just outside the Earth's atmosphere. So, why this is known as solar constant? Because this value remains more or less constant across the year. Because as we understand, in the space between the sun and the earth, there are no atmospheric particles, it is just complete vacuum. So, there is nothing which attenuates or absorbs or reflects or changes the quantum of solar radiation in that particular intervening space. However, this is not a very precise constant or like an exact constant value. There is some variation in this value around the year, and the majority, the reason for why this variation happens is due to two major reasons. One is that the earth's orbit is elliptical in nature, slightly elliptical. Not to a very large extent, but slightly elliptical in nature. So, it is not a perfect sphere. That means the earth sun distance, that is not constant throughout the year. There is some variation in that. That is one of the reasons why this solar constant is not exact constant. And the second reason is that the solar activity also fluctuates around the year. So, the solar activity is also not constant. From time to time there are solar flares, sometimes it increases, sometimes it decreases. So, the solar activity is also not constant. So, due to these two effects, a rough estimate of variation of the solar constant is that it varies somewhere in the range of around 3.4% plus minus on either side. So, that means this value of solar radiation just outside the Earth's atmosphere might be changing in the range of somewhere around 1320 to 1400 watt per meter square, almost in that range, just outside the Earth's atmosphere. But we treat it, the average value we take as the solar constant around 1366 watt per meter square. But still, if you see, this is fairly steady amount of radiation which we get outside the Earth's atmosphere. Inside the Earth's atmosphere, the story is very different. We will come to that shortly. Now, in this variation also, when you look at this variation from 1320 to 1400 watt per meter square, the interesting thing is that the radiation intensity is highest in month of January and lowest in the month of July in this range outside the Earth's atmosphere. Now that might seem a little counterintuitive for people in the northern hemisphere. Like for us in India, we see that January is the winter season and we have a lot of fog and the radiation intensity is actually lower, whereas June and July is the summer season and monsoon season and intensity is relatively higher. So for that we need to understand a little bit in terms of the orbit of the earth and the tilted axis of the earth. So if let's say this is the sun here, and let's say this is the orbit of the earth around the sun. Now as we understand, earth has a tilted axis, so something like that, and it goes around on the tilted axis around the sun. So if we consider the middle line of the through the earth globe, that is the equator, so January is close to the winter solstice. So this is, let's say, the winter solstice, and at that point of time the sun is directly overhead on the Tropic of Capricorn. In the southern hemisphere. And then gradually, so this happens somewhere around December 21, and then there are two equinoxes. So there is one equinox when the sun is directly overhead on the equator, the spring equinox March 21, and the another one is the autumn equinox around September 21, when the sun is directly overhead on the equator. And in between here we have the summer solstice, which happens around June 21, and at that point of time the sun is directly overhead on the Tropic of Cancer. So due to this phenomena, for us, for people in the northern hemisphere, we feel the solar radiation intensity higher in the summer season around the May-June time, whereas in the winter season for us, that happens around December and January. So that time the southern hemisphere of this earth is facing the sun. That is why the radiation intensity is relatively lower for us in the northern hemisphere. But the situation is different outside the earth's atmosphere, because then we are talking about the average intensity just outside the earth's atmosphere. So this value, the lower value happens somewhere in around July, and the higher value that happens somewhere in around January. So that is the situation just outside the earth's atmosphere. Now let's enter inside the earth's atmosphere and see what are the effects which come into picture, so that we can understand how does the terrestrial solar radiation is characterized. So there are some effects which come into picture as we go inside the earth's atmosphere, and if we are interested in the terrestrial solar radiation, so the solar radiation intensity at any location on the earth depends on several factors. So let's look at some of those broad factors. So first one is the latitude of the location. So as we just now saw in the previous slide, that with respect to observer on earth, the relative position of the sun keeps changing. So at the winter solstice, the sun is directly overhead on the Tropic of Capricorn. Then the spring equinox, it comes directly overhead on the equator. Then the summer solstice, it is directly overhead on the Tropic of Cancer. Again, autumn equinox, it is directly overhead on the equator. And then again, winter solstice, it is directly overhead on the Tropic of Capricorn. So that way, the relative position of the sun with respect to the different latitudes on earth, it keeps changing. But throughout the year, if you see, the sun is always in the tropical zone. From Tropic of Cancer to the Tropic of Capricorn, the sun is directly overhead somewhere in that zone. It is never directly overhead beyond that, the tropical zone. So that is why latitude of location becomes quite important. So if someone is located in the tropical region, from the Tropic of Cancer to Tropic of Capricorn, at least at some point of the year the sun will be directly overhead for them. But if you are beyond the tropics, between the tropics and the poles, then at no point of time in the year would the sun be directly overhead on your location. So what that implies is that for all the locations which are beyond the tropics, the sun's rays will be falling in an oblique manner throughout the year, and because they are traveling through a longer path length through the atmosphere, the radiation intensity would be lower. And that is a common observation also, that the solar radiation intensity is the highest in the tropical region, and as you go towards the poles it is lower. So that is the first factor. Second one is the season of the year and time of the day. So these two are also very important. So as we just now saw, for a person in the northern hemisphere, summer season is the time when the sun is directly overhead, so radiation intensity is higher. Winter season is the time when the sun is directly overhead on the southern hemisphere, so in the northern hemisphere the intensity is relatively lower. Same with the time of the day, as is common observation, all of us have seen. So in the morning when the sun rises, the intensity is very low. Gradually the intensity picks up. It peaks during the midday, then gradually it again goes down and it is lowest around the sunset hour. And after the sunset, from the sunset hour to the sunrise hour, it's almost completely dark. So time of the day, it's a very common observation which each one of us observes every day. Apart from the latitude and the timing, there are few other important factors. So third is the atmospheric effect. So atmospheric effects are very, very interesting and important, and we'll be looking at them in a little more detail in a short while from now. And fourth one is the local variations in the atmosphere. So there are some localized effects. One is the overall atmospheric effect, another is the localized variations like the amount of water vapor, clouds or pollutants in the atmosphere present at a particular location. So these are some of the major factors which impact the amount of terrestrial solar radiation. We will be looking at these two, atmospheric effects and the local variations in the atmosphere, in little more detail. So what happens when the sun's radiation travels through the Earth's atmosphere? There are two major effects, so to say. One is there is a reduction in the power density of the radiation, and the second one is that there is a change in the spectral content of the solar radiation. Now the reduction in power density, that happens due to three effects. So there are three phenomena which come into picture here, which come into the play here. One is absorption. So absorption, there are different gases in the Earth's atmosphere, as we understand. Some of these gases, they are able to absorb a lot of radiation at some particular wavelengths. So some of the most important gases in this context are ozone. As we know, the ozone layer protects us from the ultraviolet radiation. Apart from that, water vapor, carbon dioxide, as we all know, one of the most important greenhouse gas, GHG emission, CO2, and also oxygen to some extent. So these all gases, they have a very significant absorption of solar radiation at particular wavelengths. Another effect is scattering. So lot of these atmospheric particles and aerosols which are there in the atmosphere, they scatter the solar radiation. Scattering means, let's say if there is a particle like that and solar radiation hits that, it is scattering the radiation into different directions. And the third one is reflection. So there are a lot of atmospheric particles or types of clouds which reflect the radiation back into the outer atmosphere, especially the clouds which are at a very high altitude in the stratosphere or very high regions of the atmosphere. They can reflect some radiation in the outer atmosphere as well. So due to absorption, scattering and reflection, there is a reduction of power density of the radiation in the Earth's atmosphere. And the second thing is the change in the spectral content. So now what happens that these gases which we mentioned, they do not absorb radiation in a uniform manner. These gases and any other gas for that matter, it is sensitive to radiation at a particular wavelength. So there are some specific wavelengths which are absorbed to a larger extent by these different gases, be it ozone or water vapor or CO2 or oxygen. So due to that, what happens that the nature of the spectrum that changes as the radiation passes through the Earth's atmosphere. We'll come to that change in spectral content in a short while. But before that, let's look at a little bit more detail in terms of the reduction in the power density of radiation. What is the effect of different components of the atmosphere, how they reduce the intensity of the radiation in the atmosphere. So let's look at this. So this particular figure, it very interestingly summarizes the effect of power reduction or reduction in the intensity of solar radiation as radiation passes through the Earth's atmosphere. So as you can see, there are different layers in the atmosphere, and at the top here you see there is input radiation which we are calling as 100%. So this is nothing but the solar constant or the radiation outside the Earth's atmosphere, which we just now saw. It is around 1366 watt per meter square. So that is the input just outside the Earth's atmosphere. That is what is entering the Earth's atmosphere. Now on the left hand side of this funnel type structure, you see there is the total absorbed radiation which is around 18%. So 18% of the radiation is absorbed in the atmosphere. The breakup is also given here. Highest absorption is by air molecules which are almost absorbing 8% of the radiation, and in the entire height of the atmosphere from 0 to 30 kilometers this phenomena happens. Next one is water vapor, which absorbs roughly around 6% of the radiation in the lower region of the atmosphere from 0 to 3 kilometers. Then you have a lower dust layer, again in the lower region of the atmosphere in 0 to 3 kilometers, absorbs around 1% of the radiation. There is an upper dust layer in 15 to 25 kilometers height, and that absorbs another 1% of the radiation. And finally you have the ozone layer, which is at a height of 20 to 40 kilometers in the atmosphere and absorbs around 2% of the radiation. And the total, if you sum it up, comes out around 18%. So that is the absorption. On the right hand side of this funnel, you see the breakup of scattering. So there are again different regions, they are having different amounts of scattering effects. But to summarize, if you see the total radiation scattered towards Earth is 7%, and also what we call as the reflected is nothing but scattered back to space. So the total radiation scattered back to space is around 3%. So if you see 18 plus 7 plus 3, 28%, or if we round it off, roughly around 30% of the radiation is lost in the atmosphere. So what comes direct to Earth is 70%. But there is a caveat here, we should be aware of that. So this is not a stagnant thing. It is not that everywhere all the time the same breakup of radiation will be there. This is very important to understand. This particular breakup of radiation is under one specific condition, and that is mentioned here on the left hand side of this slide. So it is under typical clear sky conditions. Okay. This is a very important word, typical clear sky condition. What it means is that when there is no cloud cover. So if you have a completely clear sky condition, there is no cloud cover and the radiation is traveling through the atmosphere, then this type of breakup would happen. Roughly 18% would be absorbed by the atmospheric layers, 7% would be scattered towards the Earth, and 3% scattered or reflected away from the Earth. And only 70% of the radiation would come as a direct beam radiation towards Earth. So that is the situation under typical clear sky conditions. But one major phenomena which changes this accounting of radiation is the cloud cover. So as the cloud cover happens, if the clouds come into the picture, if there is a cloud cover happening at a given location, then this radiation balance changes very drastically. Now, before we go to the impact of that cloud cover, we need to understand that this thing, what we are calling as scattered towards Earth, this is what gives rise to what we call as the diffused radiation. So, in the outer space outside the Earth's atmosphere, there is no diffused radiation, it is only direct radiation or beam radiation. But when the radiation travels through the Earth's atmosphere, due to these effects which we just now discussed, there is a scattering which is happening, and that gives rise to diffused radiation. Whereas there is a direct or beam component, so this is known as the direct radiation. Now, if you see under typical clear sky conditions, this ratio of direct to diffused, as you can see in this figure, 70:7 or 10:1. So, roughly that is the ratio of direct to diffused radiation under typical clear sky conditions. But as the cloud cover rises, what will happen, that as cloud cover rises, your direct radiation goes down and diffused increases. So, this ratio would change, it would not remain 10:1, it might become, let us say, 8:1, it might become 5:1, 2:1. So, it can go on changing like that. And interestingly, if you have a complete cloud cover or completely overcast sky, that means there is a complete cloud cover, then in that condition your direct radiation might become 0 completely, it will only be diffused radiation. So, that is another very important effect which is there due to the atmosphere, that there is an introduction of a diffused component in the radiation, and as the intensity of the clouds increases, as the cloud cover becomes more dense in nature, the optical density of the clouds increases, then the direct radiation goes on reducing, and under complete overcast sky conditions the direct component as well might be 0, with only diffused component of radiation being there. So, that is a very important effect which comes into picture. In this regard, there is another very important concept which we must be aware of before we move ahead towards looking at the actual spectrum of the solar radiation, how we receive it on the Earth. There is one very important concept of air mass which we must be aware of before we go to the further details of the spectrum and the radiation intensity. So, air mass is an important concept in this context, and let us first define it. So, air mass is defined as the path length which light takes through the atmosphere normalized to the shortest possible path length. So, air mass is nothing but the path length which light takes through the Earth's atmosphere, but it is not measured in meters or kilometers or any distance unit. Rather, it is measured normalized to the shortest path length through the atmosphere. So, whatever is the shortest path length through the atmosphere, we take that as unity 1, and compared to that, what is the ratio or what is the length which the solar radiation is taking at a given instant, that is the air mass. To understand this better, let me explain with a simple schematic diagram. Suppose this is the Earth's surface, and let us say this is the atmosphere, layer of atmosphere over the Earth. Now, the shortest path length will be when the sun's radiation is coming directly straight through the atmosphere perpendicular to a particular location. So, this will be the shortest path length. At any given point of time, it will be making a longer path length through the atmosphere. So, what we said, as we just now said, the shortest possible length, we will define that as unity 1. So, air mass is nothing but this length. What is the length which the radiation is taking at a given instant relative to the shortest path length. In this context, this angle becomes very important. So, at a given instant, what is the angle between the vertical and the beam radiation of the sun? So, this is defined as the zenith angle or theta z. So, this zenith angle is important in this regard, defined as theta z. So, if we do a very simple trigonometric exercise here, so let us assume perpendicular here and we write this cos of theta z, this will be nothing but 1 by air mass, and therefore, air mass comes out to be 1 by cos of theta z. So, that is the air mass. At any given instant, for an observer on earth, whatever is the location of the sun, so if you join a hypothetical line from the sun's center to this observer, or basically the beam radiation which is coming from the sun to that location, the angle made by the beam radiation to the vertical, that is the zenith angle, and air mass is nothing but 1 by cos of theta z. So, as you can see, because we know that cos theta z, any cosine of any value cos will be always between 0 to 1, maximum value is 1, minimum is 0. So, as per this, what we understand that air mass can be at least 1 and can go up to infinity. So, air mass will always be greater than equal to 1. It will be equal to 1 when the sun is directly overhead at that location, the path length is at its minimum. At all other times, the path length will be longer, and the value of air mass tells us how big the path length is. So, if air mass is 2, it means that the radiation is travelling twice the length as compared to the shortest path length through the atmosphere. However, there is one exception to this. Though if we look at it mathematically, we see that air mass will always be between 1 to infinity, minimum value is 1, higher can be anything higher than that. But there is one exception to this, and that is air mass 0. Yes, though that might sound very surprising to you, mathematically it does not make sense. Cos theta z can never be infinity. So, how come air mass is becoming 0? So, it is beyond this equation. If you look at the equation, air mass is only between 1 to infinity, but conceptually air mass can be 0. And how is that possible? So, you look at the definition. Air mass is defined as the path length which light takes through the atmosphere. That is very important, through the atmosphere. So, we define air mass only when the light is travelling through the atmosphere. So, if we consider the position just outside the Earth's atmosphere, that is the place where light has still not entered the atmosphere. So, that is where the path length through the atmosphere is 0, and that is where we say air mass is 0. So, mathematically air mass can only be 1 or higher than 1, but only other exceptional value possible is air mass 0, which is just outside the Earth's atmosphere, where the path length through the atmosphere is 0. So, with that, let us quickly look at this particular figure. Before we end today's lecture, one last concept we should look at is this very interesting comparison. So, in this figure, if you see, there are 3 curves. The green one is the ideal black body radiation at 5800 Kelvin, the same temperature which we considered for the photosphere of the sun. So, that is like the ideal black body radiation at 5800 Kelvin. The red one is AM0 or air mass 0. This is just outside the Earth's atmosphere. So, the spectrum of sun outside the Earth's atmosphere is given by AM0, and whereas AM1.5 is like the standard spectrum for solar PV applications on Earth. And what you see here is that the red curve outside the Earth's atmosphere, there is intensity is higher, whereas the blue curve there is a significant reduction, and if you see, the major reduction is happening in the ultraviolet region. So ultraviolet region, that is where the ozone is, eating up almost entire ultraviolet radiation. Also in the visible region, ozone is active, it can absorb radiation in that region also. And then there is water vapor, oxygen and CO2, which are putting those deep cuts or troughs in the spectrum. So the blue curve is the radiation, the spectrum which we receive on planet Earth, whereas the red one is just outside the Earth's atmosphere. And the reduction which we see from red curve to blue curve is the atmospheric effect due to the absorption, scattering and reflection of radiation in the Earth's atmosphere. Whereas the green curve is the idealized curve for a black body at 5800 Kelvin. And that reminds me, in one of the classes when I was teaching this course, one of the student asked very interesting question, that if black body at 5800 Kelvin is given that green curve and we are saying AM0 is just outside the Earth's atmosphere, then why these two are different? Because we don't have anything between the Earth and the Sun. There is no atmosphere, there are no gases, there are no particles, it is just complete vacuum. So there is nothing to absorb the radiation, nothing to scatter the radiation. Then how come that green curve and the red curve are not exactly the same? So that might seem an interesting question, but to remind you, you should consider what is the origin of these two curves. So the green curve is just a model of a black body, which is ideal black body at 5800 Kelvin, whereas red curve is a measured radiation just outside the Earth's atmosphere. So what we said, if you recall in the initial lectures, is that Sun can be approximated with a black body at 5800 Kelvin. So it is very approximate, close by, but it won't be exactly the same, right? So that is the reason why the green and the red curves are also different. So that is it for today's lecture, and hope to see you in the next lecture where we will delve further deeper into the concepts of solar radiation. Thank you.